Hi gents, we're gonna have a look now at some context and applications. This is again from our excellent sample paper here. These are really important questions, ones that we would have been spending quite a bit of time on if we were in school, because these are longer questions. It's a different skill to just section one, here's a question, do a question, that sort of stuff. So what I want you to do is I do want you to spend quite a bit of time on these. You got to really pay attention to the first couple of questions because if you get those wrong, typically it all goes horribly wrong. In this case, I see they actually give you the answer to part one. That has become more of a theme as they're doing, because they realize that if you can't do the first bit, it's kind of unfair that you'll lose out on 50 marks or whatever it is going. Just remember with all these, pause it beforehand. Try it out, however long the video is, you're meant to be spending quite a bit longer on that due to pausing it. Obviously you can come back to it as well. It doesn't have to be in one sitting or anything like that. Okay, I think this sort of question is quite likely to come up. It does come up generally, but since it involves exponential growth, given everything that's been in the media recently about it, I would think that that's a pretty topical thing for it to come up. In this case, we have the population of a species of flowers after t years is given by, so it's sort of a function, okay? You can either put in p and find out what t is, or you can put in t and find out what p is. And a really common thing that they do is they give you this and then they say, at the initial conditions, what was the story here? There's a constant which often we have to find at the beginning. Initial conditions just means that t is equal to 0. A really, really common thing that they do is starting off giving you that t is equal to 0, giving you the population, and you just find out what k is, what is the constant. So that is actually what happens in this case. Given that there are 500 flowers at the start, so at the start, that's important that you can translate that into t equals 0. So we got 500 is equal to 3000, and it's k times e to the 0.25, what's 25, we'll write that in, 25t, where t is 0, and it's over 1 plus k times e to the 0.25 times 0. Obviously that's going to be e to the 0 is just 1. So that's a really common thing for them to start off with. Look out for it whenever you see it. So it's 3000 times k, and it's e to the power of 0, which is just 1, so we'll just leave it at that, and it's 1 plus, and it's going to be k times e to the power of 0, so that's just k times 1. So again, we can just leave it like that. Multiply both sides by 1 plus k, so we get 500 times 1 plus k is equal to 3000k. So we get 500 plus 500 k's is equal to 3000k. Might have been faster to divide both sides by 500 actually on the previous go, but I missed it. So we get 500k is, we get 500 is equal to 2500 k's, and k is 500 divided by 2500, and that is 0.2. So what I would do now is I would actually update up here, I would update my function or my formula. It's 3000 times 0.2 times e to the 0.25t, and it's over 1 plus k, which is again 0.2 times e to the 0.2, I don't know why I said 25, sorry, just 0.2 t. Oh, sorry, it did say 0.25 up there. 0.25t. Okay, so we have now stuck in what is the value of k. I think actually, to be honest with you, it is worth doing that 3000 there multiplied by 0.2. They are just multiplying each other, so it is okay just to say that that is 600 times e to the 0.25t, and down here 1 plus 0.2 e to the 0.25t. Okay, from here on, typically what they will do, so we'll just say P equals that. Typically what they'll do is they will either give us the population and get us to get out the time, or they'll give us the time and get out the population. Or maybe they'll be asking for, you know, how things are growing or increasing or something like that. We might have to do some differentiation or something along those lines. But typically they'll give you one, get the other. So let's read this. That's exactly what they do. Use the equation for P to find the number of years after which the population is 1, 2, 3, 3. So they're giving you what the population is. Okay, it's 1, 2, 3, 3, and it's equal to 600 e to the 0.25t over 1 plus 0.2 e to the 0.25t. There we go. In this case here, you might have been able to do some cancelling or something like that, dividing top and bottom by that, except for the fact that it's 1 plus. Okay, obviously you wouldn't want to divide top and bottom by e to the 0.5t, because t would just disappear in that case. It's not even possible, but the reason that it's not possible is because it's 1 plus. But sometimes you will be able to do that and it'll actually be useful, but not in this case. 1, 2, 3, 3 times 1 plus 0.2 e to the 0.25t is equal to 600 e to the 0.25t's there. So we get 1, 2, 3, 3 plus 1, 2, 3, 3 times 0.2, which is also multiplying e to the 0.25t. You can put the bracket there, or since they're all multiplying, you can put it there. 600 e to the 0.25t. Okay, the reason that I wrote it like that is because I think it is probably better to write it as that. Is it? Maybe, maybe not. I don't know. But here, 1, 2, 3, 3, we've got that. When we go and multiply 1, 2, 3, 3 by 0.2, we end up getting 246.6 e to the 0.25t's, and it's equal to 600 e to the 0.25t. These are the same terms as each other. It's like having 246.6x equal to 600x. You can just subtract 246.6x from both sides, or in this case 246.6 e to the 0.25t's. So we get this is equal to, and really just on your calculator just have to do 600 minus 246.6. So we get 353.4 e to the 0.25t's, and you want to just have e to the power of something first of all, so we need to divide both sides by 353.4 and this side by 353.4. So 1, 2, 3, 3 divided by ANS, since I have it on my calculator already, is not a nice number at all. So what to do here? I suppose what we could do is we could say it's 1, 2, 3, 3, 0, multiply top and bottom by 10, just to write it a little bit nicer. And this thing is just e to the 0.25t. What we want to do now is we want to do ln of both sides. So I'm going to take the natural log of this side. So 12330 divided by 3534. Yeah, on my calculator that says 2055589. You don't really have to change it. And it's equal to ln e to the 0.25t. So we get t ln e, 0.25t, I should say, 0.25t times ln e. That's the rules of logs. And here we have ln 2055589, and it's divided by, well, it will be divided by 0.25 because ln e, as we know, is 1. So we get t when we're dividing this by 0.25, and we get ln 2055 over 589 divided by 0.25. So t is that. So let's see, we should get ln of the answer, and we should divide that by 0.25. And we get t is equal to 4.998. So I think it is fair to say that they're looking for something along the lines of t is equal to 5. I might even just say t is approximately equal to 5. So we got 5 years there for it. Okay, there's our answer. As you can see, it doesn't quite fit into the B part at all. Okay, use this value of k. Using this value of k, fill in the table below, writing the values of p to the nearest whole number. Okay, so the value of k, I presume the value of k that they want is they want us to continue using 0.2. So in this case, what you should do is you should, you can just float it into the equation. Okay, you know what, is it k that we're trying to get, or is it, sorry, it's p that we're trying to get. So we have what k is. Okay, k is 0.2, and they're just getting us to put in the times. So you've got on your calculator a mode which will allow you to actually just do that straight away, because we're only putting in 2, 4, 6, 8, 10. So you could actually go and create a function on your calculator using that function button, and go from there. So if you're doing that, remember you want the starting value to be 2, and you want the increments, what it goes up by, to be 2, and it'll create a little table function for you. So I'll go ahead and do that. Okay, having done that, when we place 0 in, we get 500. We actually knew that one already. We might zoom in on this so it's a little bit clearer. After 2 years, you will have, so I think it asks p to the nearest whole number, so that's 744. So when it's 4 years in, it's 10. It says 57 here. It says 1056.5. So I'm going to guess that's 1057 without any. I assume it hasn't like gone and rounded that up to 0.5 or anything like that on me. 1789.2. I noticed just on my calculator that it only gives it to one decimal place. So you know what, I wouldn't mind, that was our table function, by the way. I wouldn't mind just taking a second just to type in, which one was the 0.5 one? I think it was this one, question, or number 4, place that one in there and just see what do we get. So let's do that. 600 e to the 0.25, and I'm putting in 4 here, and it's over 1 plus 0.2 e to the 0.25 by t, which is again 4. Yeah, so that comes up as 1056.56. So you would just need to be a little bit careful there. That's fine. This is to the nearest thing. But I imagine if it had been 1056.49, it would have on the tables thing said 1056.5, in which case you might have rounded up, understandably, whereas actually you should be rounding down in that instance. That's just a little something to be careful of. If they're a good designer, they won't let that happen. But you never know. Okay, use these results to plot a graph of p against t on the grid shown. So at t years, we have 500. At 2, we've 744. Okay, so let's see, about here is about 750. So 744 is really close to that. So we'll say that it's, sorry, we're on 2. That's around there. For 4, 1057. Okay, well, let's think about what each one of these are. So this here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, as per is normal. There are 10 there for 5 runs, so each one is 50. Okay, so each one is 50. So 10, 57. So you're looking at pretty much there, since each one up is going to be 50. So is with 4. I see here, sorry, we were meant to do that to a whole number. So that's that. I was thinking about whether to round up or not. So 1418. 1418. That's around about there. For 8, it's 1789. Okay, so that's 1750. So it's just a bit above that. Line there, so around about here. And this one is 2 1. Okay, 2 1. Have I missed out on one? I haven't. No. Okay, 2 1 2 7. So about halfway in between there and there. Okay, so actually this is what we end up. This is what we end up getting. Okay, I didn't quite go through the points, so I will try that one again. Third time lucky. Okay, that's what we should be looking at roughly. Okay, use your graph to find the population after 7 years. So this is important. When they say use your graph to, what you really have to do is you actually have to show it on the graph. You have to show that you haven't just typed this into a calculator in order to get out the answer. So what you should be doing is you should be going to 7 years with a ruler, which I can't do on my screen. You should be reading up. It hits the graph there as far as I can see on my thing, and you should be reading across. Again, use a ruler and a pencil just to show the examiner that that is what you've done. Okay, so that comes out to me as 1600. Okay, use your graph to find the population after 7 years. P is equal to, I'm getting 1600. Now, of course, there's nothing to say that you can't just sneak onto your calculator and throw in 7 for T. Now, I already have it set up from having double checked the 4, so I can do that, and it comes out as 1605. So you can see here that we're really accurate based on that. Obviously, if you type in 1605, if you write that on your exam, it's going to be very obvious that you've gone and cheated with it. So please be careful with that. Question 2, calculate algebraically the population of the nearest whole number after 7 years. Okay, well, that was actually just what we did. But they say algebraically. I find that a little bit weird. What sort of algebra are they looking for us to use? I mean, really what we're just doing is we're just putting that in. I wonder, will the E part help us show by manipulating the equation at the beginning of the question that P is equal to this? Okay, so that involves a bit of algebra. So maybe if D is not just throw in the number, maybe this E part is going to be helpful. So let's just remind ourselves what the equation was at the very beginning, because I've sort of lost it. We get P is equal to blah 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 blah. Okay, P, so 600 E. Okay, so we had that it was 600 e to the 0.25 t over 1 plus, I think this was 0.2 e to the 0.25 t, and I think that was equal to p. So it's hard to do, as you can imagine, like this. Go away, box. I'm making a total mess of it now, sorry. Yeah, that's what we have there. Okay, so that's the bit of algebra that they want us to manipulate. So rather than zoom into the box, I will just do it here. So we get 600 e to the 0.25t over 1 plus 0.2 e to the 0.25t, and it's equal to p. Lost a t in there again, is equal to p times, and here we have 1 plus 0.2 e to the 0.25t. So I'm imagining what's going to happen here is we're going to have, as you can see, this one only has one e in it, so we're going to have some sort of coming together with the e's. So I'll be multiplying this thing out. This is very much a case of you trying to do this, as I keep saying, probably to your annoyance, is you should be pausing the videos to try this rather than, you know, just having me look at it or something like that. So go ahead and go and do that, is what I would say to you here. Okay, what do we have? I suppose if we did say that we want the e to the 0.25 to be interacting, then we should probably get them over to the one side. E to the 0.25t, and here we have minus p times 0.2 e to the 0.25t, oh, it's equal to p. Okay, e to the 0.25t. Maybe a good idea here just to go and factorize it. Okay, so we end up getting 600, that's a good sign, and we end up getting minus p. Sorry, minus 0.25 is minus 0.2 p's. That. Okay, so we get that, and that is equal to p. So it looks to me as if we are on the right track here. Hopefully that is the case. So what can we say here? We can say that e to the 0.25t is equal to p over 600 minus 0.2p. Now it's been a little bit tricky here so far. It's been a little bit tricky as to what we should do. So this one, how do we get just p on its own? Okay, it's not such an easy question as to how we would go about getting that, but I think I see now that there was maybe a faster way to do it, but we shall go with it here. To get just one single p, you should divide top and bottom by p itself. So we get 600 over p minus 0.2. So you could just go about it like that. Okay. There's another thing here. If we write this thing as a fraction, okay, this, to be honest, it's not the this isn't the nicest thing I've ever done in terms of working stuff out, but look, it'll work. It'll work as we do it. So here what we have is we've got a fraction equal to a fraction. So we've said before, if you've a over b is equal to c over d, you can multiply both sides by bd. So the left is going to be AD, the left is going to be CB. And now what you can do is you can divide both sides by, for instance, if you've divided both sides by A, you would get D is equal to CD over A. And now if you divided both sides by, let's say C, yeah, you would get D over C is equal to D over A. And I should have said all of that thing apart from, let me just try that again. I messed that up. Multiply both sides by BD, I beg your pardon. AD is equal to BC. That is what I should have been saying here in this case. That was a bad one. Now, what I'm really trying to do is I'm trying to show that B over A is equal to D over C. So I'm just trying to show that the opposite thing here is true. So since we want C on the bottom, we would divide both sides by C. We would get AD over C is equal to B. And you can see here, this is almost the thing that we want. We wanted D over C, so I'll divide both sides by A. We get D over C is equal to B over A. Hey presto, we've shown that. So if the upshot of all that is, if you've got a fraction equals a fraction, you can flip the top and the bottom. Not very good mathematical way to say it. Instead, that's why I took my time out there, just to show you the one thing was the other. So in this case, what we can say is we can actually say that 1 over e to the 0.25t is equal to, and this is 600 over p minus 0.2, and that's over 1, if you like. Okay, that's over 1, if you want to think of it like that. Okay. So we can now use the rules of, what am I trying to say? Not logs, indices there. So you've got 1 over a to the m, and it's equal to a to the minus m. So here we can say that this thing is e to the minus 0.25 t. And that's good because that is something that crops up in our work here. And here we have 600 over p minus 0.2. So what we want to do here is we really want to multiply everything by p because it's meant to be p equals. So we've p times e to the minus 0.25t is equal to 600, and we have minus 0.2 p's here. If you do find that you have 2 p's and you want to only have one of them, bring them all to the one side and factorize. So we have p times e to the minus 0.25 t plus 0.2. There we go, that's the thing that we want. P is equal to 600 over e to the minus 0.25 t plus 0.2. So there you go. P has popped out, and it's exactly what we wanted it to be. Now, that said, this is certainly not the nicest way to do this. Okay, this is certainly not the nicest way to do this. So partway through, I saw that there was a much neater way to do it. So I'm just going to go and do that now. So this is one way to do it, but it's a lot of lines, as you can see. So let's just go back up to our very starting position and see, can you come up with, while I'm rubbing it out there, can you come up with a better plan, just a faster plan to get this thing to happen? I can see a much faster plan right there in front of me. Yeah, it's funny, after you kind of see the plan, you're like, what on earth was I thinking, jumping around doing all of this? But of course, it gives you the right answer, and you should be able to do it anyway. But look, we're so close to this thing that we want to get here. We're so close to it. Maybe if I'd written it as, instead of having it there, oh, for some reason my screen doesn't want to be able to rub it out. Now it does. Maybe if I'd actually written it like this, you can see that we're so close to it. And in fact, here we have the exact thing that we want. Okay, almost the exact thing that we want. We want 600. So what would we have to do with this? Well, we just have to divide it by e to the 0.25t. Maybe you saw that straight away. So that's what we'll do. We'll divide top and bottom of the fraction. So we don't have to do it left and right, just top and bottom of the fraction. We'll divide the top by e to the 0.25t. We just get 600. And the bottom, because we've got an addition going on, it's both things that have to be divided by e to the 0.25t. So we get 1 over e to the 0.25t. And then on this side, we just get, well, it's 0.2 times e to the 0.25t divided by e to the 0.25t. So that'll just leave you with 0.2. And look at that, how embarrassing. We get 600. 1 over that, we've already said, is e to the minus 0.25t. And here we just get 0.2. So there we go. Maybe it was worth it as I was taking down from above. I had that equals p, you know, just psychologically or something like that. If you have it written like that, maybe you're much more likely to go and see that that's what it is. But this is, of course, employing Cusack's principle. Okay, if you want something, get it. From there, we're very close actually to the thing that we want now that we see that. So what would I need? I want 600. What do I have to do? And the plan will come up. Okay, so just make sure that you have the t in there so that it's actually the thing that they're looking for. And of course, writing it like this also makes it much easier to place numbers in. You're not having to put in 7 in twice, whereas here there's t is in there twice. So it's just that little bit more efficient to have it written like that. To go back to part 2 where it says calculate algebraically what the population was, the only thing I can see here is you can put in 7 in there. Of course, you can put it in here. That's sort of doing it out of order to what they've asked. So it's probably just better just to put it into the top one, though I don't actually think there will be a problem. I did that already, and I think, as I recall, the answer was 1605 from that. Okay. All right. There's even more stuff here. Okay, so this is to do with limits. God, it's quite a long question. F parts, G parts, and all the rest of it. You can see here they've also managed to ask lots of different types of questions. Okay, find the limit of or to the n for which the absolute value of or is greater than 1. Okay, and it asks, use this to show that p can never exceed 3000. Oh, sorry, yeah, so this is still tying in, I beg your pardon, this is still tying in with our previous one. When they talk about p, they're talking about this p here. Okay, so they're asking us to show why the population can never be 3000. So if we flick back up here, I think you can see that 3000 is going to be something of an issue as we do. Okay, so let's just talk about this because limits are important and it's been a while since we've done it. Okay, so if we have that the limit is now or has to be greater than, so if we say 2 to the n as n heads to infinity, I think you can see what happens here. Okay, when we place infinity in here, you can't obviously, but what we're saying is as n becomes really big, where does this thing head towards? Well, it heads towards infinity. Okay, so we're saying that will be the case. You got to be a little bit careful here. It says or if the absolute value of or is greater than 1. So let's just think about this. Could or be minus 2, for instance, or could be minus 2. So just be a little bit careful with minus 2. What's the story here? So in this case, where is it headed towards as it goes to infinity? Well, it's not headed towards one particular place. So when you put 1 in, you get minus 2, but then you'll get 4, then you get minus 8, then you get plus 16, but you'll get minus 32, plus 64, minus 128. It's not headed towards a particular place. Okay, it's swinging. It's getting, in one half, it's getting closer to minus infinity, and on the other, it's going to plus infinity, but it's not going to one particular place itself. Okay, so if we were saying that or is greater than 1, what we would be saying here is we would be saying infinity, but in this case it's not, so you just need to be a little bit careful of that. Yeah, so just make sure that I paused it and unintentionally unpaused it partway through. I don't know if I'll be able to remove that. Probably not, because I don't have the technical ability. But just I was just having a bit of existential crisis based on what the question was asking. Because it didn't seem like they wanted us to write in that the limit doesn't exist. But look, I've double checked it there and just was making sure I wasn't being crazy or anything like that. This thing here is allowing or to be a negative number, okay? Because if you put in -2, the absolute value of -2 is greater than 1. So -2 would work here. And sure, if or is positive number and greater than 1, it is just simply going to go up to infinity. But if it's a negative number, because it's going to be squared, cubed, etc. It's -2 multiplied by -2. You're continually multiplying by a negative number, so you are flicking up between plus infinity and minus infinity. Okay, so it's not going to a particular place. So the answer that I would give is very technically true answer is that the limit does not exist. Now, after me loading these papers, we might just have a little bit of a chat about this. It says the answer is infinity. That would be true if or was strictly positive, but I actually suspect what they meant to ask. Was that this thing is less than 1. So what that would mean is that or has to be between 1 and -1. So it's some sort of fraction in between 1 and -1. Well, in that case, if you've got a fraction, like half or something like that. Sorry, if it's a half, I'm jumping ahead to what I'm going to be thinking of. If it's a half the power of n, as n increases here, it's a half, a quarter, an eighth, a 16th, and so on. That is getting smaller and smaller and smaller. It is heading towards 0. So I suspect that's the question that they wanted to ask was what's that doing? Okay, that's obviously the person I just double checked to make sure I wasn't lying to you when I said that it doesn't exist, and it doesn't. Now, what if it's a negative here? Do we run into the same problem? We do not, because we will have minus a half, but then we'll have plus a quarter, then we'll have minus an eighth, then we'll have plus a 16th, then we'll have minus 1/32th, or whatever you call that, 1/64th. It's still heading towards 0. So even if it's negative. So it just has to be between 1 and -1 in order for it to go to 0. I suspect that that's what the question wanted, because it specifically says use this property to show that p can never be above 3000. Now we got what p was. P is equal to 600 over e to the -0.25t plus 0.2, like that. And it wants us to get the limit of p as t goes to infinity. So we just have to see, if we were to place infinity in here for t, what would go on? Well, it's better in this case, instead of calling it e to the -0.25 t, it is better to call it e to the 1 over e to the 0.25 t, and then add on a 0.2 as you would do here. Now what's happening? Okay, when we make t really, really gigantic, infinity, or really huge number here, we're going to get e to a gigantic number. E to a gigantic number. E itself is actually, you know what? Maybe they did mean this, and they were just wrong with it. But for me, it does not exist. Okay, that doesn't exist because of the technical point. If it came up in the leaving cert, just say if or is greater than 1 and positive, and that's already included in that, then the limit as n goes to infinity is infinity. Okay, you can say that. I'm going to work the n as n goes to infinity is that. You can say that. So in this case, e, which is 2 point whatever, so it is positive and it is greater than 1. In that case, because it's that to infinity, it's going to become really huge. So e to the power of that, that's going to be a gigantic number. When you then have 1 over gigantic number, that heads towards 0. So this whole thing here heads towards 0. So we could say that the limit itself, since that thing is headed towards 0, as you approach infinity, that approaches 0. We get 0.2, and we end up, I'm going to say that that divides into get 3,000. So you can see that it will never go above 3,000. In fact, it'll never hit 3,000, because of course you will never go to time equals infinity, but that is where it's headed towards. It is headed towards 3,000, so it can never exceed 3,000. Okay, so that I think is the way that I would be writing that. Okay. Right. G, find the rate of change. Like I said, there's only so many things that they can ask you about this. So in this case, they're asking you for rate of change. Okay. When t is equal to 1. Rate of change, anytime you see that, we're talking about f dash of x, or in this case, it's f dash of t, or dy dx, or whatever it is that you want to call it. And after that, you let t equal to 1. Do not do it before that, do it after that, and find it the nearest whole number. So I'm just wondering now, is it best, as you can see, I haven't been fantastic at judging what the fastest way to do these things are. We'll get it right, all right, but I think just if we do the division 1 here, quotient rule, minus 0.25t plus 0.2. So we're going to call this bit u, we're going to call this bit v here. That I think is just maybe the fastest way to do it. So du dx, there's a few others that I can think of. dv dx is that. Okay, important that you can remember how to differentiate these things here. So whenever you have e, you should write it down immediately again. Whatever it is, just write it straight down again, and then you multiply by whatever that thing is differentiated. So that is minus 0.25 times it, plus 0.2, that becomes nothing. Okay, and now it's just a matter of getting out the quotient rule. F dash of x, in this case it's f dash of t, the rate of change. F dash of t is equal to, well, there's a formula, and for quotient rule it is v du dx plus u dv dx, and it's all over v squared. Now it has been a while, so I suspect that I'm just having again a moment of, am I remembering this off the top of my head? I think it might be subtraction. Yeah, I'm going to say that it is. Don't have my tables book just to hand. It is of course in there, but I'm pretty sure it is that. Okay, v du dx. Okay, so we have e to the minus 0.25t plus 0.2 times du dx. That is 0. And then we get minus, well, we're going to find out pretty quickly whether we're getting a good number or not. U, which is 600, times dv dx, which is minus 0.25. That looks good because we've a minus by a minus now, so that's going to give us a positive, which looks sensible. E to the minus 0.25t all over v squared. So that's e to the minus 0.25t plus 0.2, and that thing is being squared. Now obviously 0 by that is gone, so we just have 600. So there's going to be a lot of things to type in here. Should we? Yeah, we should probably make this a little bit easier. So we'll say 150 e to the minus 0.25t. Down here, there's not much you can do with that, really. Plus 0.2, and it is going to be squared. Okay, what we want to do in this case is we want to say what's f dash of t when t is 1. So you just put t equals 1 in there. So we will go and do that. So it's 150. It is going to be e minus 0.25 adds 1. And here we have e to the minus 0.25 by 1 plus 0.2 close brackets, and the bottom bit is going to be squared. So this to me comes out to be, did they say nearest whole number? They did. 1, 2, 2. I don't know what happened to my computer there. Okay, that is what the rate of change is. Now, what does that mean? If you are asked, and I don't know if they did, they didn't. If they ask you that there, if they say, what does that mean in the context of this question? That means that after 1 year, okay, after 1 year, the rate of change is such that when you move over 1, you're going up, you know, it's rise over run. At that exact instance, when you move over 1 unit, you are going up 122 units. So as you move over 1 year, it's rising by 122 flowers. Okay, that's the sort of question that they might ask inside the whole thing. Okay, I wonder if it's best. Yeah, I think it might be best if we just throw it there. I know that was a longer video than is normal, particularly for one question. But even though I paused, actually, I tried to do fewer pauses inside that than what I would normally do.